Welcome. Today we are going to see about permanent magnet moving coil instrument, PMMC instruments. Okay, these instruments are otherwise known as PMMC instruments. Okay, these instruments are being used to measure the voltage and current, which is being of DC supply. Okay, it is basically a DC instrument. You cannot measure AC voltage and current in this instrument. You can only measure DC voltage and DC current using this permanent magnet moving coil instruments. So you all know what will happen when a conductor is placed in the magnetic field. Okay, if there is two magnets, one is north pole and another one is south pole, and you are having a metal conductor present in between the north and south pole, if you are applying a voltage to this conductor, you are connecting to it to a battery. Okay, then the current will be flowing in the conductor. Okay, so this current I, which is flowing in the conductor, will create a electromagnetic flux. Okay, this magnetic flux is created by the permanent magnet. Okay, when the current is flowing in the conductor, an electromagnetic flux will be created surrounding the conductor. So this magnetic flux, which is created by the electromagnet and as well as the permanent magnetic flux, will interact with each other, and this conductor will experience a force and it will tends to move in a direction. So this is the basic principle of permanent magnet moving coil instrument. Here there are two magnets, north and south. These two magnets are permanent. They are not going to move anywhere. Whereas here is the moving coil, which is going to move according to the amount of current or voltage which is being measured in the device. This is the basic concept of permanent magnet moving coil instrument, and this is known as de-Arsenoval movement. Now let us move into the permanent magnet moving coil instrument. Here you are seeing the two magnets. One is the north pole and another one is the south pole. Okay, these are the two magnets, and in between the two magnets you will be having flux lines of force passing into them. Okay, next you are having a shaft. Okay, here is the shaft. You can see this one is the shaft. This is connected at the top end with the help of a pivot and a bearing. This is one bearing. You can see this bearing is present here, and similarly at the bottom end another one bearing is present. Okay, so these two bearings hold this shaft in a steady manner. Okay, next in this shaft you are having a magnetic former. Okay, here is the magnetic former. You can see this one is the magnetic former and this one is the core. Okay, here you are going to wind the coil, that is the uh, coil windings will be present here. Okay, this coil windings will helps us to magnetize the former, and the two outputs from the coil will be present here. Okay, next you are seeing that the former is attached with the spindle. Okay, this former is attached with the shaft here, and the shaft is attached with the pointer. Okay, and this pointer is being connected, which indicates the value of current or voltage which is present in the scale over here. Okay, so this is the basic construction of the permanent magnet moving coil instrument. Next you can see how this works. Okay, since the pointer is very long, so you need to have a counterweight. So for the counterweight, you are using a balance weight at the end of the pointer terminal in the reverse side. Okay, next you are seeing there are spring. Okay, here is the spring. Okay, why this is being used? Spring is being used as a controlling torque to provide controlling torque to the pointer. Okay, let us this is the basic construction of the permanent magnet moving coil instrument. Okay, now let us move to the operation of permanent magnet moving coil instrument. The image that you have seen earlier, this one is the side view of the permanent magnet moving coil instrument, where this image is the top view of the permanent magnet moving coil instrument. Here you are having the two magnets north and south over here, and you are having the balance weight, and here is the center shaft. Okay, here is the shaft, and the bearings is present in the top side. Okay, the bearing will be present in the top side. Okay, here the pointer is shown. In the pointer you are having the balance weight, and here you can see the spring. Okay, here is the spring. Okay, this one is the spring. Okay, spring. Okay, next you can see the scale arrangement and the mirror arrangement to reduce the error. Okay, this mirror is being used to reduce the error while you are reading. Okay, this is the basic constructional arrangement. Here you can see the soft cylindrical iron core. This is the core in which the winding is being wound in the transformer. That is the core of the permanent magnet moving coil instrument. Okay, next we will see how this works. Okay, from the windings present here, you will be having two outputs. Okay, you have to supply the voltage or current being measured. If it is an ammeter, you are going to supply the DC current which is to be measured, and the scale is measured in amperes. Whereas it is a voltmeter, the scale will be in voltage. Okay, so we are going to supply the required quantity. It should be a DC quantity. It should have the polarities. Okay, one end should be the polarity positive and other end should be negative. Okay, if you supply this voltage or current into this transformer where the coil is present inside the magnetic flux created by the permanent magnets, you can see the flux which is created by the permanent magnet is passing from north pole to south pole like this. Okay, if the supply is being present in the former will create a magnetic flux around it. Okay, this magnetic flux is going to interact with the flux which is already present, and it is created by the permanent magnet. So the interaction between the two fluxes, one flux is the created flux and the other flux is the flux due to the permanent magnets. According to these two flux, the pointer starts to deflect. So this deflection is created by the This deflection is created by the current or voltage which is being passed into the coil present in the former. So this deflection is directly proportional to the current. Once this deflection is made, the pointer will directly move and it will hit the end position of the meter. So it will not show you the reading. If a small amount of current, say 1 milliampere of current is being fed into this, at once the meter will read the last value. Say it is 10 amperes. This will lead, it will show you 10 amperes. If you give 2 milliamperes of current, then it will show you 10 amperes. Why this happens? Because there is no control in the movement of the pointer. If you apply the voltage or current, at once the pointer will deflect and it will reach the end. It will be like a motor. Okay, if there is no end, it will start to rotate as a motor. To avoid this, what you have to do, you need to give a counter force to stop the pointer in the measured value. Okay, so to do it, you need a controlling torque. So the controlling torque is provided by the spring. Okay, so the spring will provide the reverse force, and this spring will bring the pointer to the correct value in which you are going to measure. That is, the amount of current or voltage being fed into measure will be indicated in the pointer and the scale when the controlling torque exerted by the spring is equivalent to the deflection torque. So the deflection torque TD is given by the current which is flowing in the former, whereas the controlling torque TC is provided by the spring, that quantity. So this is done by the spring. Okay, next, you know that there are three torques. Okay, one is the deflection torque, which is produced by the current or voltage being measured, and there is another one torque, which is the controlling torque, which is created by the bronze spring, Posper bronze spring. There are two Posper bronze springs present in the permanent magnet moving coil instrument. One will be at the top near the top of the bearing, and another spring will be at the bottom position near the bottom of the bearing. Okay, there will be two bearings, one at the top and other at the bottom, and this is the pivot. Okay, here will be one spring and here will be another one spring. Okay, these two springs helps to indicate the current values exactly or the voltage values exactly which is being measured. And here there is the extra one torque which is known as a damping torque, and it is produced by the eddy current flowing in the former. Okay, what is mean by damping torque? You need to know this. Okay, okay. Assume you are going to supply 10 volt of voltage and you are providing the voltage in the instrument. Okay, the current corresponding to the voltage will be flowing into the former. Okay, and the pointer is going to deflect. Okay, from the zero position it will going to deflect to the 10 volt position. So while this deflection happens, the pointer will not sharply stop at 10 volt. It will first deflect to 12 volt and it will return back to 8 volt. After that, it comes to 11 volt and it again return back to 9 volt, and the pointer will have a swinging tendency like a pendulum. Okay, so before attaining the steady position, that is the 10 volt, which is indicated by the pointer will deflect back and forth before getting to the steady position. So to attain the steady position at a faster rate, to avoid swinging of the pointer, uh, we are going to use another one torque. This torque will minimize the swing of the pointer from back and forth. This torque is known as the damping torque. Okay. This damping torque is produced by the eddy currents flowing in the former. This is the current. If you are supplying a, you're having a coil like this, and you are supplying a voltage uh, plus 10 volt. Okay, what happens is the current which is flowing here will induces a magnetic field, and this induced magnetic field will cut the former. This former is also made up of a conducting material. So this conducting material, while it is cut by a magnetic flux, and this magnetic flux will create a current in this former. This current is known as the this current is known as the eddy current. So eddy current will help us to give the damping torque which is required to stop the oscillations present in the pointer while measuring the quantities. Now let us move into the torque equation. So the torque equation is deflection torque TD is equal to NBAI. Okay, let us see what are these things. TD is the deflection torque produced by the amount of current which is being measured. Okay, it is the unit Newton meters. Okay, the N is the number of turns of the coil. In the former, if you are having 100 turns, then you should substitute 100 over here. Next, A is the effective coil area. So the amount of area covered by the coil in the former, it is measured in meter squared. I is the amount of current flowing in the former or the coil. This is the current I which is flowing in the former, and B is the flux density created by the current. So this is the basic working, construction and operating principle of permanent magnet moving coil instruments.